Now this let's look a little more closer into paper chromatography. See, paper chromatography is yeah. You consider this. Yeah, consider there is a two components. Component let it be component A or like a two components. See, this is one component, and this is again another component. So when it is moving, yeah, it will start to separate. It will start to separate. It will slowly. It will start to separate. So you can see it will separate, and once it reaches here, this will separate out here. Two components it is separating here. Okay, this is one component. Component let it be component A, component B. So how this separation is being achieved is, you should know one thing, that this is a chromatography paper. So say this component, I mean the one which is green component, this will be loosely bound with this chromatography paper. So as the solvent it is passes, this component B it will flow a little more easily. Because there is a less interaction between this component B and paper. On the other hand, this component A it got more interaction. Due to that, this component A it will bind very tenaciously. So the moment it will become slowly it will go. On the other hand, the component B, since it is bound nicely, it will go fast. It will bound leastly, it will go fast. Okay. So this is how this paper chromatography steps it will be working. Now, actually, how the paper chromatography it will be using for identification of different components. See, say you are having some amino acids. Amino acid. It is not colored. Okay, it is not colored. So in order to separate the amino acids, what we can do is, so say, suppose this A component it will contain more amino acids. I really don't know how many amino acids are present, maybe 2 or 3. So B, we are taking some mixture B, C and D. So this contain one amino acid, this C also contain one amino acid, D also contain one amino acid. Okay, say the same chromatography procedure we can follow. So you consider you take a beaker and you are holding a chromatography paper. So you put while you are cutting the chromatography paper, you just draw a line using the pencil. Okay. So through this line, you take this A, B, C or D. You will just mix it with some proper solvent. You can actually, I told you, the solvent we will be using, it depends on the separation, depends on the compounds we are trying. For amino acid, you can use acetone and water, or like a mixture of acetone and ethanol also you can use. So now this component A, using a small micro needle, just prick. See, consider this containing component A. So component A you mix it with the ethanol. Okay. So using a needle, you just apply this spots on component A here. Next, using the needle, you can apply here at B also, C also, D also. Okay. Now this is something you need to do it. You apply one spot at B, A, B, C and D. Now what is remaining is you can take this paper and you can put it inside a beaker. So this is a mixture of acetone plus water, or like acetone plus ethanol. Okay. The same way, of course, it will start to move. And now take out the paper. So this is A, B, C and D. Now take out the paper. You can just observe it. So this is a pencil line. Okay. So you can see that the solvent might have raised and up to here. So this is the solvent front. I mean the distance traversed by the solvent front. Okay. So yeah, let it be component A is having, this is component A. Component A is separated and come up to here. Component B is yeah, component B, it is up to here. Again component C, A, B, C, yeah, up to here, and component D, yeah, it is up to component up to D here, right? Okay. So suppose from here until here, this is the distance the solvent traveled. So let it be 1.2 centimeter. Okay. So this is the distance traveled by the component respective components. Okay. And yeah, one thing what you can understand is like see, there is yeah, I forgot to mention something, that this paper, no, that you cannot easily see this which one, I mean like this amino acids by the naked eye. You need to use some specialized technique. See, once this distance is traveled by traveled by this amino acids at a particular distance, okay, then the next job is actually like you need to observe it actually till where and this amino acids might have traveled. So there are some coloring agents or like visualizing agents are there which we need to use in order to make this amino acids to be visible. So you take out the paper, you will be spraying the same way I have sprayed for cleaning this board. Okay, I will be spraying using the, suppose this is the paper, this is the chromatography paper. So not using the hand, of course, yeah, we will be spraying. So once we spray this coloring agent or like visualizing agent, this spots, it will be visible. Usually for amino acids, the coloring and the visualizing agent we will be using is an inhydrin. There is a visualizing agent, we call it as an inhydrin. That is actually a neurotoxic agent. You need to be very careful while we are spraying that. So that agent is called an inhydrin. Okay. So once we spray it, of course, these spots it will be visible. Now let me see. Actually, this is the let it be 1.2 is the distance traveled by solvent. So that we will just note it. This is the distance traveled by the solvent. So this spot, let it be component A, it contains two components, A1 and A2. So A1 might have traveled some 0.2 centimeter, maybe this A2 might have traveled 0.8 centimeter. So that also we will note it actually, distance traveled by this amino acid moieties up to where this amino acid moieties have traveled. So there is one particular retardation, the constant we call it as a retardation factor. So this is called a retardation factor. This is actually we can calculate the distance traveled by amino acids divided by distance traveled by the solvent. Okay. Yeah. Now, like for every amino acids, this R factor it is going to be constant. For example, like for cysteine, this R value is 0.08. For lysine, it is 0.14. Say like glycine, it is 0.26. Serine, it is 0.27. So just by calculating this retardation factor or R factor, we are able to identify what is the amino acid, which is the amino acid present in it. Okay. So in order to calculate which is the amino acid present in it, it is really possible. Like we can use this as sports and we can calculate it. Okay. So if we look closely into this paper chromatography, there are many ways, even in forensic sciences, even in food detection. Sometimes, yeah. For example, like your food, you take a food, say milk or like cereal or say some other animal proteins, okay, animal food like meat, some chicken or like beef, or say you will be taking a small amount of beef, okay, this is a small amount of small piece of beef, so you will grind it and you will add some ethanol or some solvent and mix it properly. Then using the paper chromatography, you will be able to tell like what amino acids are present in that. So this is the application of paper chromatography even in food industry, even in what like this forensic sciences, even in many applications. Okay, you will be able to tell actually what is which amino acids are present in it. You will be able to tell. That is how the applications of paper chromatography it goes. In fact, this paper, as I already mentioned, that is stationary, right? It is not moving. So it is actually the stationary phase. In fact, this is solvent, it is moving. We call it as a mobile phase. Okay, we can call it as mobile phase. The paper which is we are using, it is called a stationary phase, right? In fact, not paper. If we are speaking holistically, it is nothing but the cellulose. Cellulose is the stationary phase. This solvent is the mobile phase. Okay. There is some exercise questions at 25. So the first question is explain in your words, explain in your own words how paper chromatography work. Yeah. If I tell you how the paper chromatography working is, see, like it is between the interaction between the stationary phase and the mobile phase. Suppose these two are the first. This is stationary phase. Yeah, this is stationary phase and this is mobile phase. This mobile phase, it will be keep on interaction with the stationary phase. So the something which we need to separate, it will be in the mobile phase, right? So obviously that also will be in a constant interaction between this stationary phase and mobile phase, and the distance it is traveling, it will be different. So that is how the separation it attains. What do you think of a locating agent? Second question. What do you think a locating agent? Locating agent in the paper chromatography is for amino acids, it is ninhydrin. See this ninhydrin, how it is able to locate the amino acid is, see, consider a paper. This is an amino acid spot. Okay, this ninhydrin, it will bind with the amino acid. Okay, it will bind with the amino acid groups. Say like ninhydrin, if I put N, amino acid if I put A. So N and A, it will bind to form a complex. Okay, it will bind to form a complex, and what to say, like that, and we are able to locate it. Now, why do you need one in experiment to separate amino acids by chromatography? We need a chromatography to separate amino acid. That is the question. So the answer is because chromatography is a very efficient technique. Of course, there are many techniques, filtration, distillation. Say like what is the reason is. See, I will tell you this amino acids. If I tell you two structures, see, this is a glycine. NH2COOH. This is the simplest amino acid. Glycine. So this is alanine. Okay. Glycine and alanine. See, what is the difference between both? Only one methyl group. So do you think it is a big difference? No. It is just with a very minor difference is that. Otherwise, all the groups it is remaining same. So one thing what you need to understand is this glycine and alanine. It is very chemically similar. Obviously, its properties are also going to be similar because it shows the properties of carboxylic group as well as amino group. Okay, NH2 group. Okay, and yeah, now. So its interaction with the paper also going to be very similar. So we need some very cutting edge or like very precise experimental technique to separate this glycine and alanine from each other. Okay, so that is the reason we are using paper chromatography. Okay, so like something which is having very closely related molecular structure, chemical structure, we need to separate using paper chromatography, right? And what makes RF values, next question, third question, what makes RF value is so useful. Yeah. Of course, RF value is constant for an amino acid. So like just by measuring the RF value, we will be able to tell what amino acid it is. Okay. For the chromatogram above, the one we were showing, where any of the amino acid one we were showing previously. Fourth question, for the chromatogram above, where any of the amino acids in B to E also present in A, how can you tell that? Yeah. Suppose you consider this chromatography paper. So this is A, right? So let it be. Suppose this is B. Yeah, this is A. This contains 2 amino acids. Okay, B mixture contains 1 amino acid. So when we check it, suppose if any amino acid is present, suppose if the same amino acid in B is present in A, like we can easily tell that. After the chromatography, yeah, we will identify the spot here. Here, A, it is having 1 spot here, next spot here. In this case, see, the distance traveled by the component A is similar to B. Obviously, what you need to understand, so this is the same amino acid which is present here in A also. So the component is same, right? Component remains same. This is something you need to know. If it is not, suppose this spot is present somewhere here, then we can say these two are, I mean like A1 and A2, it is 2 different amino acid. The B1 or like B component, it is again another amino acid. Okay, suppose if the distance is traveling between 2 components, it is same, it is remaining same, that is shows it is a same amino acid. The same amino acid present in B is present in A also. This is something you need to know. Use the RF table above to name them. Yeah, suppose they are using the question, using a ruler, work out the RF value for the amino acid in A to E. Yeah, like I don't want to go into that. See, like suppose if you run a chromatogram and if you calculate RF value, you will be able to tell. Yeah, there is a standard chart for every amino acid. The RF value will be having a particular value. So there is a standard chart using which you can tell. Yeah, this is cysteine, this is alanine, this is glycine, and this is isoleucine and tryptophan. So which amino acid is that? You will be able to tell that. Okay.